In this video, we are going to begin our discussion of the method of reduction of order. For this method, it only works, and this is the downfall to this method, is we have to be given a solution to a nth order, any order, linear homogeneous ODE. What that means is, we have the linear ODE, and then the homogeneous part tells us that the right-hand side has to be equal to 0. Okay, so given that, we have that. And we know that we can write a general case because of the second order, and there's some theory to this, and I don't really focus on the theory too much in this case because most of my students are engineers going forward with this into a bunch of different fields. So I've been advised on multiple levels not to go too heavy in the theory, but what this tells me is that since this is second order, then this symbol means there exist two solutions, y sub 1 and y sub 2, such that we can write that general solution in that form, right? The theory tells us that if I have those, I can write that and get a general solution. So we're going to use that idea. If I have one solution, y sub 1, this is only for the homogeneous case, but if I have that solution, we can use this method to find that other y sub 2. Okay, so the idea comes from this. In the theory, they mention that the two solutions have to be linearly independent. Let's talk about if they were dependent. What that means is they would be a multiple of each other, meaning that I could take y sub 2, take some kind of constant, and multiply it by y sub 1. Take y sub 1 and multiply it by a constant and get y sub 2. That's what I meant to say. That's what that means, is that this is a constant. But this says independent. So if it's independent, that means if there is another one, and I know I can get it this way, I'm going to put a u there, then this u, to create this new function based on y sub 1, this u is not a constant, right? It is a function of x, or whatever our independent variable may be, x or t, whatever it is. So with that idea, we are going to work off that idea not being a constant, but this being our solution, or the form of our solution, where we have some function times y sub 1. We're going to use that as a solution and evaluate derivatives and plug it in and try to solve for that u. All right, so let's take this with an example. Your notes won't have this scribble through it. I'm not going to read through the method. I'm going to work through the method, and then you can read through the method and see where we went through that whole thing. The method's there to help you. Just so you know where we are going, and I'm going to keep saying this, I'm probably going to annoy you with it, is we're just going to keep taking that DE that we saw at the beginning of this right up here, and we're just going to keep making it more complicated, taking stuff and putting it on the right-hand side like we're doing 0 right now for the homogeneous case, and we're going to work into putting other things over there on the right in different forms. So this method stuff is a good thing maybe to write down in your notes if you need to be completely organized, right? Reduction of order, here's the method. Right, reduction of order, this is what it looks like. Maybe this whole page right here would be a good point and one example. Make yourself some reference sheets. That way when you go to study for your exams, you can, oh, okay, I don't remember what reduction of order is, right? When you're studying for your exam, you're talking to yourself, what is that method, right? And the more you can shove into your brain for a long-term method, right, to get it memorized, the better, obviously. If you can get it in there, memorized, and have all these differentiated in your head, that's ideally where we would want to be, because you would soundly know how to work within a DE. And that's our goal. Is a lot of you are engineers. You're going to work with specific DEs that you're going to become extremely familiar with, and it's not going to feel like that big of a deal. That's kind of the point here. The further you can get into here, the further that's going to feel more natural when you get to that point in your career. All right, so let's take this and see where we can go with it. Okay, so y sub 2, by this theory, they said take some function u and times by y sub 1. All right, so that's some function u times t to the negative 1. I just picked that up from here. All right, I have y sub 2. We also would like y sub 2, maybe the first derivative. This is a power rule, so we get u prime times t to the negative 1. minus u times t to the negative 2. It's just a product rule. Y sub 2, we do our second derivative of that. So now we're going to have two product rules. So u double prime times t to the negative 1 plus u prime, it's going to be a minus though, minus u prime t to the negative 2. Minus, okay, so minus, I'm going to put it in parentheses because now it's going to be a product rule, u prime times t to the negative 2 plus u, the negative is going to come down for that, negative 2u t to the negative 3. So we have that. All right, we're going to have to plug all this in. So I am going to multiply this out, that negative through, just so I don't have to do it later. It's negative 2, make sure not to make mistakes here. That'd be so defeating. All right, so there we go. We have that. Now we're going to plug it into our dE. So here's our dE. 2 times t squared. So 2t squared times, and we plug now our second derivative in. U double prime times t to the negative 1 minus u prime t to the negative 2 minus u prime t to the negative 2. We could have put those together. Let's go ahead and do that. So that's a minus 2 u prime t to the negative 2. If we don't do it now, we'll have to do it in the next step, which means more writing. Tu 2u t to the negative 3. All right. Then we got plus t times, and then we throw our first derivative in, u prime t to the negative 1 minus u times t to the negative 2 minus 3 times, and then it's going to be u times t to the negative 1 equals 0. Okay, you check your work with mine, and hopefully we're right. I'm going to double check with my notes because I know my notes are right because I got to the answer there. So I'm double checking. You're looking for mistakes within your own work. Looks like we're good. Okay, so that's all good. So now I'm going to distribute. So we get t u double prime times t minus 2. We have that distributed already. Minus 4 u prime plus 4 u t to the negative 1 plus u prime minus u t to the negative 1 minus 3u t to the negative 1. Sorry I didn't list all that out and talk about it. Just read it off to you. It's just algebra. Okay, so now I have this, and we are looking for things that are going to go away. So I'm going to highlight things that maybe cancel out. I have 4u t to the negative 1, and then these two make a negative 4, so those are gone. And then those can be added together. So I have a u double prime t minus 3u prime. Okay. Now if I divide by 2t, all right, u double prime minus 3 over 2t times u prime equals 0. All right, so now this is where the reduction of order, notice that this is it's hidden, and I'll make it more obvious in this next step. This is actually a first order linear ODE, homogeneous ODE, with respect to u prime. Okay, what I mean by that is we're going to go off here and we're going to say let u prime equal w. Then u double prime is equal to w prime. So I'm going to make those substitutions. All right, so that is w prime minus 3 over 2t, nothing there changes, and u prime is w equals 0. So notice now, this will be, sometimes it's separable. I believe this one is not separable. Sometimes they are, so you could look for that. Just be very careful. I have found myself working quickly before thinking, and I'm like, oh, that's definitely separable, and then I just make it separable for some reason and mess it up. So just be careful, go slow. if you want to never take that wrong route of separable, it should always be first order linear. Okay, so if it's first order linear, that means I need a mu. That's my integrating factor. That's e to the integral of the coefficient of w. So this is going to be a negative integral, or negative, let's go ahead and do a negative 3 over 2, integral of 1 over t dt, right? So we get e to the negative 3 over 2 ln of t. That is t to the negative 3 halves. I can drop the absolute value because that's a half power, which means it's a square root, right? So if it's a square root, it has to be positive anyway. So I'm going to drop the absolute value. Okay, so that guarantees that. That is my integrating factor. So I'm going to multiply my dE now by that. T to the negative 3 halves times W prime minus, okay, so this has to be multiplied by that. We still have minus 3 over 2, but we're going to have a 3 over 2, and then the negative makes it go down. That's a 1 on the bottom. It's a t to the 5 halves on bottom times w equals 0 to 0. Right-hand side doesn't change when I multiply by that. Okay, so I have that now. That is d dt times should be our integrating factor times w. You should check and make sure that works out. My notes match, so I'm going to move on from that. Take the time to take the product rule there and make sure that it does work out to the line before. Remember, that was the whole point of our integrating factor. Let's write that integrating factor here. Okay. Now, we can take the integral of both sides. This is just solving a first order linear. So hopefully you guys have it down at this point. dt, integral of 0 dt. So we get t to the negative 3 halves times w equals, okay, and this ends up being a c. We multiply by t to the 3 halves, we get w equals c times 3 to t to the 3 halves. Right, since we are just looking for another solution that's going to work here, we don't want a general solution. I can just find another y, and I'm going to put a c on it anyway at the very end. So what I'm going to do here is I'm going to choose c to be 1 just to help with my work for the moment. And then we can think about some other numbers later if we need to, and we will in this problem. So I'll show you what I mean. Okay, so now recall that w is equal to u prime. So u prime is equal to t to the 3 halves. So if I want u, I take the integral of t to the 3 halves dt. So u is equal to, okay, that's going to be a 5 halves, which gets me a 2/5 because I'm dividing by that. Plus, all right, and we got another c. I'm going to call it c1 here. All right, we're going to choose that c1 because we're going to have that same scenario. We're going to multiply by another constant later, and we're going to multiply c1 by another constant and call it something else. So I'm just going to call it a 0. Okay, so we have a 0 then. That tells me that y sub 2 of t is equal to, okay, we know that that is equal to u times y sub 1 of t, right? Well, I have u, 2/5 t to the 5 halves. I'm going to leave that no c, right, because we let that equal 0. And then times y sub 1, which is t to the negative 1. All right, so y sub 2 is equal to, okay, we get 2/5 t to the, okay, that's a negative 2 over 2, so that's going to be 3 over 2. Now, we know from the theory way above that we can write this as a general solution given that y sub 1 and y sub 2 are linearly independent, and this method guarantees that they end up being linearly independent. So what I was saying earlier is I'm going to actually, let's call this y sub 2 star. Actually, let's just call it that. Y sub 2, I could call y sub 2 star here. I'm just going to call it t to the 3 halves. And the reason I can do that is because when I write down my answer, y equals c1 times t to the negative 1, that was y sub 1, plus c2 times t to the 3 halves. If I were to take this 2/5 with me, it would just get absorbed into the constant, right? If I have a c2, a constant, times 2/5, I get a new constant. So I can drop a constant like that if it's being multiplied. Sorry, I just tried to box this, but I can drop the constant from the front if it's being multiplied, if it gets absorbed into the other constant. All right, so there's our solution. The reason that we can do this is because we had a second order homogeneous linear ODE, and we were given a solution already and we're guaranteed that we have two solutions that are linearly independent. Using that idea, and given that there are only two solutions, then we can work this out to get a new solution. Like I said, it's hard to find examples of this. If you need practice, I think in our homework we only have like 2 or 3, maybe 4, I think, at most. If you need to find them, Google reduction of order problems. You'll actually probably find the ones I picked for this lecture on that. Just go find them. Make sure when you do look for them and you're trying them, find ones that have a solution for you, meaning already worked out. A good example of that would be a solution manual to a book that maybe we use, the one that we're using the sections out of. I know I don't reference a whole lot of notes out of it. There are things I'm pulling out of that thing, and certain homework problems. If you would like a solution, some solutions to some problems out of the homework, all you gotta do is email me and let me know, and I can send you parts of their solutions to some problems so you can get some extra practice.